Hi everyone, this is Miss Dunn. Hopefully you guys are all feeling well, getting outside, not letting schoolwork take over your lives, but still getting it done. I'm just going to go through the slides that I went over on Thursday afternoon with some people who could show up. So if the slides say things like, chat with each other, that may not be applicable. That's totally fine. I was curious how you've all been feeling, something good that's happened. Any feedback on online learning in general would be very welcome. That said, let's just get into Chapter 19 notes. So Chapter 19 is about climate change. So at any point, if there's something interactive where I ask a question, or in this case the do now, feel free to pause the video and think about these questions to yourself. It's always better to kind of actively engage with the content for your memory, as opposed to just passively listening along. Alright, so during class on Thursday, people talked about past changes in the climate like Ice Age, how those changes were natural, but people weren't quite sure what caused them, and how today's climate change was anthropogenic, so that is caused by humans. And that was one major difference, but we'll find that there are others as well. Alright, so without further ado, Chapter 19, Climate Change. Something that's kind of been on our minds this whole time, but we haven't talked about in quite the amount of detail that the AP will get to. So the core case study for this chapter is about the island of Greenland melting, despite its name. It's mostly covered with ice as opposed to grass, and it's covered in glaciers. So if you don't know, Greenland is that large area on the northeast side of Canada. It's the world's largest island, and it's covered mostly by glaciers. Glaciers are just a fancy name for ice that's on land. That's all they are. And we might have learned in a couple chapters ago now that most of the world's freshwater is contained in ice sheets and glaciers. So Greenland has 10% of the world's freshwater. However, as you can see in the picture on the right, it's been melting over many years, and the melting is actually getting faster over time. Most of the sea level rise is due to the heating of water, because water, like most things, expands when you heat it up. But a sixth of the current rise is actually just due to Greenland on its own melting. And as we'll talk about later, this is kind of a positive feedback loop as well. But if the melting continues at the rate that it's been going, as you get to the center of Greenland, there are thicker ice sheets and glaciers. They're very large glaciers. And then if it continues, the water will rise a full meter just from Greenland on its own by 2100. And that's kind of the benchmark year that we use for a lot of these things. But it's not that far away. Most of us should be alive to see it. So the three big ideas for this chapter are about global temperature rise, the fact that temperatures are getting warmer on the Earth, not just weather, but in terms of climate. The second big idea is that this is caused by humans, it's anthropogenic. And then third, the effects of climate change, which we definitely have talked about, as well as the solutions that people propose. During the case study, you'll look at evidence for global warming, the history of international cooperation, as well as potential solutions. So, climate change. As its name implies, it talks about climate and not weather. This goes back to Chapter 7. So if weather is what you get on a day-to-day basis, what you see in the forecast, climate is what you expect. These are patterns that form over usually multiple decades. And it's agreed upon, not just by scientists, I think, or not just by scientists, but like the data show very clearly that average temperatures and greenhouse gas levels both are rising. This is kind of hard to counter when the data from many organizations around the world all say the same thing. Sorry about that. Let me turn this off. That was automatic. But the more contentious point, maybe, is that this is happening at a higher rate than usual. Again, this is not contentious among scientists. Scientists generally agree. More than 90%, etc. There is scientific consensus, more than 95% even, that this is happening at a rate higher than usual. And this is, again, something you can see in the data pretty clearly. Sometimes people will stop agreeing with this line of thought when they say it's due mostly to human activity. Way back in the biogeochemical cycle section, we saw that the carbon cycle, humans were only actually contributing a small amount, but the effect was actually very big because the ecosystems are normally in balance, and then the humans are throwing it off, even with a small number. But it's also anthropogenic. This is also agreed upon by scientific consensus, and that given all this, we must take action. So you can see how kind of each step of this reasoning, people can start to believe different things. Like this first step, most people will agree with. The data show it. It's pretty hard to disagree with. When you get all the way to the end, even if you agree with all these 3 points, maybe you think the rate is not high and dangerous, so we need to do something now. Or maybe people don't feel like it'll affect them personally. For a multitude of reasons, sometimes we don't get to the final step where we actually have to do something about it. So I say that the data are very clear, so let's take a look at the data. Here is a graph from multiple institutions of the quote-unquote temperature anomaly, so how far away from the average temperature that you would expect current temperatures are. So you'll see that the graph starts in 1880, and most graphs about this will start then. That's the year starting at which we have like enough records from around the world to get like a good estimate of what the global temperature average was like. Before that, thermometers were not widely used enough that we have this kind of data. That's why that number starts there. But you can see over time, most institutions will agree, and it's clearly been rising. Like, you cannot look at this graph and say that from the period, from 1980s onward, it is clearly going up. The trend is upwards. It's very hard to dispute this. But what is commonly said is, commonly by people who maybe are skeptical or aren't sure of the whole story, is that climate has actually changed before in the past. So take a moment to pause and think about what kinds of things have changed Earth's climate in the past. Why did it change? So go ahead and pause and think about it. But basically, the climate has changed due to tons of things. Some of these include volcanic emissions. So think about how the gases, if it's greenhouse gas, how that could affect it. If it's a bunch of soot, how that could affect it. If you've heard about how dinosaurs were maybe affected by either a giant volcano or a meteor impact, that's because those big catastrophic events changed the climate, the temperature and precipitation over time. Solar input can change. The sun literally shines brighter sometimes and dimmer in other times for just reasons that we don't quite know, but the sun has like sunspots. It kind of has bright and dark spots. It changes, and that can change climate too. Continents move around, so if some piece of continent was once at a tropical region, but it ended up moving to a polar region, obviously the climate on it would change. And we know about plate tectonics from chapter 14, so that's what that is. And of course, air and ocean circulation, which are both caused by a difference in temperature of different regions. If you don't have a current blowing the sea breeze or the clouds to you, just like in El Nino, for instance, that would change the climate. So over Earth's history, 3.5 billion years, it's changed a lot. If we zoom in a little bit more and look at the past just about 1 million years, there have been many glacial and interglacial periods. This is where you think of, the Ice Age. But there wasn't just one Ice Age. There were many Ice Age. Glacial periods are when glaciers, it's cold enough that glaciers can grow. And interglacial periods are periods where glaciers are actually shrinking or retreating. If we zoom in even more, look at the past 10,000 years, and you're getting into like modern human history. This was an interglacial period. So the temperature records show that this was a period where it's normally a little bit warmer. It's supposed to be a little warmer. The glaciers are retreating. But if you zoom in even more, in the past just 1,000 years, 1,000 to 2,000 kind of, the temperature was mostly stable. But since around 1975, there have been significant temperature changes, and those changes are accelerating. So here's a graph of what I mean. You can see that the average temperature, you can see the spikes where it's warm. That means that you're in an interglacial period, and then it drops, and then that's a glacial period. And these look really sharp, sudden changes. But if you look at the x-axis, thousands of years ago, this change, if this is 10 to 20 thousands of years kind of a change. Or sorry, this I guess is better. So multiple tens of thousands of years for this kind of drastic temperature change, where drastic, can be anything from, oh darn, there's a lot of difficult math here. 7 degrees change, that's huge. But you can also have smaller drops, like 1 degree and so on. But again, over tens of thousands of years. On the other hand, if we zoom into the past couple thousand years, here is the temperature change. Again, relative to the temperature anomaly, so no change. There's a warm period people talk about sometimes, the medieval warm period, and sometimes people will say, well, there was an ice age really recently, it's supposed to be warmer now. Sure, that's called the Little Ice Age. You can look into it if you'd like, but notice that the Little Ice Age and the warm periods, we're talking fractions of a degree here. That is nothing like the significant rise that's happening really from the mid-1900s onward. This here is exponential. This is the kind of line you see, e.g. with the spread of coronavirus or so on. It's a very, very sudden change, really unprecedented in the temperature records that we have. One question you might have, or maybe should have, is how do we possibly know that what temperatures were like, 900,000 years ago, when I told you that 1880 was the time we started using thermometers? So you can pause, think about it, look at the picture. So even though the temperature records date only back to around 1880, maybe more as we go through more records, but we can actually use other techniques. So this is ice coring. This long device, they take cores of ice, these little cylinders of ice, and inside ice, bubbles actually get trapped, bubbles of air. And if you look at the sample of air inside the ice, you can see what greenhouse gases were there at that time. So if you look at how much carbon dioxide was in the atmosphere when this layer of ice deep under, Antarctica was formed, you can look at what the greenhouse gas concentration and therefore use that as a strongly correlated variable to temperature. You can kind of get a sense of what the temperature should have been like back then. Not only can you look at bubbles, but you can also look at relative percentages of the oxygen isotopes in these samples. So water is, as you know, H2O, that's what ice is. Because there's that oxygen there, you can see how much of the O's are like heavy O's. An isotope is like a heavy versus light version of an atom, like literally more mass or less mass. And at different temperatures, we actually know that different percentages of oxygen settle out from the atmosphere. So if you look at what percentage of oxygen is heavy or light, you can also get a proxy for the temperature. So ice core layers look kind of like tree rings. You can kind of see, I think the summer is the light stuff, and then every winter is the dark stuff, and it goes back. And if you can match layers from different places, just like with tree rings, you can kind of see which years were heavy snowfall, or in the tree's case, which year was a drought, and so on and so forth. And we actually have enough layers to go quite a ways back. So NASA also has a good site about this. We're kind of walking through evidence, causes, effects, solutions. If you want, this image is actually linked to their site. It's clickable on the slides if you want to go take a look at their evidence. So I wrote that it was a break for those who were there live, but if you want to take a break and pause, obviously you can do so anytime. So the second big idea is that this is anthropogenic. Humans are causing this climate change. Well, I haven't made a convincing argument for that yet, but that's all right. So we already know humans emit CO2 from many different things. This graph on the right kind of shows you where those CO2 emissions come from. Again, the yellow is that industry that you guys always talk about, big companies, factories making things. That's a good chunk, for sure. But there's also a lot of, say, transportation, electricity and heat that we use, the energy that's too cheap, agriculture, supporting e.g. the cows. And so it's clear that this spike happened around, the mid-1900s, and it's also clear that since the Industrial Revolution, these gases, CO2, CH4, N2O, carbon dioxide, methane, nitrous oxide, those emissions have also gone up. We've talked at length about what kind of things emit these gases. But just because the gases go up, how do you know the temperature goes up? Well, first, again, let's see that the data clearly show, CO2 has spiked. again, we used our greenhouse gas bubbles in the ice cores to figure that out, but you can see, this is years before 1950. At 1950, it's quite high, and then currently it is above 400 ppm, or parts per million. Recall that the atmosphere has oxygen, nitrogen, mostly nitrogen, so 78% nitrogen, some oxygen, 21%, and carbon dioxide is actually only 400 parts per million. And if you figure out what that percentage is, it's only 0.04%. Not a ton, but it has a big effect. So we know that greenhouse gases were high. And if you look at the graph of carbon dioxide levels on top here versus temperature levels on the bottom here, you can see that there is a pretty strong correlation. They're linked. Whenever one goes up, so does the other. Whenever one drops, so does the other. And this is all because carbon dioxide is a greenhouse gas, and the greenhouse effect is also something that, isn't really disputed. We all know that the greenhouse effect happens. You can't really argue about that. But you will also notice that at the end here, the CO2 level is high. The CO2 level has spiked, but the temperatures have not spiked with it. Think about why that might be. But in the class on Thursday, we kind of discussed how this is actually because it usually takes a bit of time for the temperature to actually adjust in response to the carbon dioxide levels. There's a little bit of a lag, and because this spike is just so unprecedented, there hasn't really been time for the temperature to catch up yet. So again, I'll just remind you that the greenhouse effect exists. They kind of re-emit this infrared radiation, which is heat, and long wave. Infrared is heat, that's the same thing. It's a type of long wave radiation, and that warms the part of the atmosphere we live in, which is called the troposphere. Yes, hopefully yes. But the greenhouse effect is a natural thing. Without it, we would freeze. So without the greenhouse effect, Earth would be actually at an average temperature of below freezing. So again, carbon dioxide, totally normal. Greenhouse gases, totally normal. But too much greenhouse gases, then it gets way too hot. I also want to remind you guys that the most the greenhouse gas that causes most of the warming, over 50% of it, is actually water vapor. So don't forget that. Don't just point to carbon dioxide. Water vapor is there, and it's doing most of the warming. But the reason that it's not a big deal is that it has a fairly short lifetime and isn't super strong compared to the others. So each kind of greenhouse gas, that's what the GHG stands for, I'll be using it a lot, each type has a different atmospheric lifetime. So you can see that methane will stay in the atmosphere for around 12 years. Carbon dioxide will stay in the atmosphere for 100 years, anywhere from 50 to 200, depending on the study, and nitrous oxide stays for around 114. So just think about the implications of that. Think about where does it go after it's out of the atmosphere? Like, how can it just disappear? And in contrast with the lifetime, they also have different warming potentials. We've heard from Cowspiracy mostly that as multiples of CO2 potential, so CO2 is just defined as one, methane is 25 times as strong, as potent as greenhouse gas, and nitrous oxide is actually nearly 300 times strong. And think about what the primary sources of these things are. Again, mostly agriculture, though methane also has the rotting vegetation from dams. But nitrous oxide is definitely mostly an agricultural thing, though it'll also come with the photochemical smog in cities. One last thing people sometimes bring up about why it's not anthropogenic, maybe it's just natural, maybe it's like the sun. So how do we know it's not that the sun just happens to be getting brighter? Because as we've talked about, the sun does affect climate. So we don't think that it's currently due to the sun because of some different evidence. First of all, this graph on the right, you can see that solar radiation, like the amount of light we have coming from the sun, has actually looked pretty steady, maybe even dropped if you think this is not just noise in the last couple of years, whereas temperatures have gone up. Also, the troposphere is the one that's warming up, the layer that we live in. The layer above that, the stratosphere, it has actually cooled down. This means you would expect that if it was the sun's fault, it would equally warm all the layers together, But because only the lowest level gets warmed up, the layer that the greenhouse gases affect, we're pretty sure it's a greenhouse gas thing, not a sun thing. So, there are also a lot of other natural, abiotic, I guess, factors that can play a role in climate change. So, how does the ocean get affected? Over here you can kind of see there's three kind of different things, but we've talked about how the ocean is a carbon reservoir, but also a heat reservoir. Water absorbs heat really well. It has a very high specific heat, so it takes in a lot of the heat for us and a lot of the CO2. But this kind of results in a weird positive feedback loop, where warmer oceans, in the past century or so, it's been a 1 degree increase. Warmer oceans aren't just bad for the organisms in their zones of tolerance, but warm liquids, it's a fact from chemistry, you might know that warm liquids actually can absorb less gas. So normally gases dissolve into water, but when it gets warm, less of it is soluble. It's just less gas soluble. So you have less CO2 being absorbed, which means more CO2 in the atmosphere because it's not going to the oceans, which means it gets hotter, which means it can hold even less CO2. That's your positive feedback loop. But also it holds less oxygen, and that affects organisms as well. Kind of dead zone secondary. It's like its own way of making a dead zone. Also, CO2 levels affect the acidity of oceans, so that increased acidity or decreased pH, because water plus carbon dioxide makes carbonic acid. Obviously, that not only affects zones of tolerance, but leads to things like coral bleaching, which we've talked about with the calcium carbonate. That was back to chapter 8, I believe. Other abiotic factors includes clouds. So clouds kind of work both ways. They could be considered a positive or negative feedback loop. For sure, as it gets warmer, more evaporation happens, and more evaporation means more clouds. But depending on the type of cloud formed, different kind of effects happen. So the fluffy clouds that you see, the cumulus clouds, in Latin, the pile clouds, those decrease surface temperature by reflecting sunlight away. If you've heard of the word albedo, A-L-B-E-D-O, they have a high albedo, or reflectivity. By reflecting the sun away, it keeps the ground cool. However, it just so happens that water at the higher elevations in cirrus clouds actually will make the surface temperature warmer by trapping the heat that's trying to escape. That's just how it is. So it kind of works both ways. We're not really sure how to think about clouds yet. It's complicated, I guess. And pollution can even have cloud-like effects. So depending on the chemical that's in there, some chemicals will make it hotter, some chemicals will reflect light, some chemicals will absorb light. For instance, like soot, a black kind of particle, will absorb heat and make it warmer. So it's pretty complicated, but because of the trends with greenhouse gas rises and temperature rises, we can say that it's an anthropogenic cause. And finally, we'll talk about the effects and solutions. I had some people type into the chat or just say out loud, what are some specific consequences of climate change? How might people prepare? Take a moment to think about that. And, do be specific. It's not, we can all say, sea level rise. Okay, like, specific. How do you prepare? So, obviously rapid warming is bad. Populations just cannot evolve that quickly. You need enough time to undergo evolution as a population. Mutations don't just happen all the time, so things will die. Biodiversity decreases, and think about what that does. Additionally, there's this weird thing where the harmful effects of global warming don't affect everyone equally. There might be one city on the coast or on an island that's going to get submerged, while someone living at the poles and in the middle, away from the waters, might be like, oh, the temperature's getting better for me. So people have different reactions to it because they come from different places. And there are also these complicated things of tipping points that are hard to predict. So in chaotic systems, there's the notion of a tipping point is that not everything can just go backwards. If we just got rid of all the CO2 that we accumulated now in the atmosphere, it might be too late. one way to think about this simply is like if I rip up a piece of paper, I can't just put it back together. There are irreversible things. But another example is like if most species went extinct and then we finally fixed the problem and made temperatures back to normal, the species wouldn't just come back immediately. It may be possible that it just cannot recover. So more specifically though, we've talked about things like the melting of the Arctic. So just like Greenland, it melts. However, ice in water melting does not cause sea level to rise. Only ice on land does. But that's gone down. I think every class has had a presentation on the sad polar bears by now. We have a positive feedback loop again where, first of all, ice gets hit on two fronts. There's warm air and warm water. So it's melting from both sides. And because the ice is so reflective, it has high albedo. It going away makes the warming happen faster. Additionally, there's methane trapped in the permafrost. So we've all seen the videos of them lighting, this gas coming out of the ice on fire. Methane is a greenhouse gas, so we're also contributing to the warming that way as well. Your book has nice visuals of here's the tundra. If you ever have books where the protagonists are sent to Siberia, Crime and Punishment, or what have you, by 2100 or so, we don't expect that tundra to really be there anymore. So that's taking a whole biome, changing it very much, and destroying, of course, the species that live there. So I'll show you guys some glaciers melting now. If you want to stretch, stand up. So you can see a time lapse of glaciers melting. Again, glaciers are just ice on land. So there's a glacier, and then it doesn't look like much, maybe, or maybe it does, but glaciers are huge. That can be like as tall as or taller than the Empire State. So here's a glacier in Iceland over the past 4 years. You can actually see that we're in a glacial period because you might notice the ice is actually moving towards you vaguely. It's coming towards the viewer. It's trying to slump forward just under the influence of gravity, but clearly it's being chipped away at also. So this is the same glacier, but a different time and a different angle. You can kind of see it's just melting away. It's all black because it's covered in dirt, but it's ice. Here's a glacier in Alaska. Again, the glaciers are advancing. They're trying to go forward, but the effects of climate change are such that the net effect, the overall effect, is that they're retreating. They're getting melted away. I think the next video shows a perspective where it's a little clearer because, but even if they're supposed to be advancing and they're actually just staying still, you can see the effects of climate change that way. Here's Alaska again. Yeah, you can see it's really getting eaten away at even though it's trying to advance. Alright, so ice doesn't just melt, but the sea does rise. People are saying anywhere from around a meter, plus or minus some, depending on what actions we take. Just like the coronavirus, you're not going to predict it exactly. The models will depend on what actions are taken. There will be many tipping points associated with sea level rise, so irreversible kind of effects. First of all the delicate ecosystems that live along the coast, along the land and the water, so that's your coastal zones, your wetlands, your coral reefs, those will be degraded. Think about why, explain why on the FRQ, don't just say that. But islands, those biodiverse hotspots usually, or islands, will flood. Deltas and estuaries and coasts will all flood. That will contaminate any kind of freshwater aquifers as well. And many, many cities live on the coast too. 50% of people live along the coast. Those will get flooded. So you can see this is with 1 meter sea level rise, Miami would be completely flooded. And that's, happening in this century. We've also talked about the extreme weather. I'll go a little faster because I know we've talked about this. But severe drought, once again, hotter means more water evaporates, means it's warmer because water is a greenhouse gas, means even more evaporation. You get droughts, but also wildfires because plants get dried out, but also storms because you have a bunch of evaporation that leads to more precipitation. So drought would mean that you have water tables going down, surface water declining. That affects food production, agriculture, but also just people who live on fairly limited water supplies, so climate refugees. not only does it affect people, of course, it affects biodiversity. So, for example, the Amazon rainforest, which clearly depends on its, annual supply of rain and its climate being what it is, a lot of it, a majority could be lost due to warming. And as habitat loss happens, so do extinctions. Other places that are affected include oceans. We know that algae or phytoplankton produce 50% of our oxygen, but the phytoplankton there have already declined up to 90%. And we've read articles about how insects and birds are in complete decline. And human health, we know that more mosquitoes might expand from the tropics. Tropical diseases might become more common. So, favor things that make us sick, whether that's air pollution, the smog that forms, or water quality, or, mold growing, etc. Pollution can go up, and people will need to move around, and, that'll just have effects on the geopolitical situation, etc. Just a couple more slides here, but if you need to take a break now, here's a reasonable point to do so. As we see the video on the next screen of the map, what kinds of things do you notice? What surprised you? Why is it happening? So I'll play this a few times, or I'll just play it once and you can go back and see it if you'd like. So there's the year on the top. CO2 emissions per capita. Not much is happening. Well, we'll see. Some things that people in class said included, the US is kind of deciding whether or not to be dark red for a while. Right around now, a large portion of Eurasia lights up, though I guess that might just be Russia because Russia's very big. But you can definitely see darker colors around Europe. Okay. That was the end right there, 2017, so let me just bring it over there. Someone mentioned that, China and India never actually lit up a dark red, and that's because this is per capita. This is per person. So even though China definitely has the greatest amount of greenhouse gas emissions right now, first of all, it's partly to make products that we want in the US. And second of all, they still have many, many, many people. Our quality of life is much, much higher. The US, as far as large countries go, the US and actually Canada are quite bad in terms of per capita carbon emissions. So it's definitely us. We are definitely contributing to the problem, and it's... Okay, so what should we do about it, I guess? So there are two different kinds of ways to talk about solutions to climate change. This kind of mitigation, kind of slowing it down, emit less CO2, increase energy efficiency, go for renewables, cogeneration, sustainable transportation, all of those kinds of things. We've talked about that a little bit more, I think. But adaptation is saying that, hey, some change is going to happen. That's inevitable. We're not going to stop it at this point. All we can do is do the best we can to be prepared for it. So, mitigation versus adaptation. So here's one of these slides. You can look at it on your own. But of course, this is difficult. You can kind of think of some reasons why, but really it's a global problem. The tragedy of the commons strikes again. There really needs to be international cooperation, just like with CFCs and the Montreal Protocol. That was the one that worked. Generally, it does not work. So, it can become political. It can become about one party versus another versus just what the science says and what we need to do. And because the impacts of climate change are not equal, one country might be affected a lot more than another, countries have different incentives to actually do something about it. This is something you'll explore more in the case study. But not only is it a global problem, but there are also a few other reasons. So people are just not very good at responding to long-term problems. It's kind of, we don't act until it's a little bit too late or we can see the effects. For instance, coronavirus, we talked about it back in January. We said it was exponential, it was going to get bad. of course, people didn't implement measures until it was already getting bad. There's also the story of that isn't necessarily true about how if you put a frog into boiling water but raise the temperature slowly, it won't jump out. Almost certainly not true, but it kind of illustrates the point that people won't necessarily do something about it until it's too late, or it's hard to prepare for something that hasn't happened yet. Also, there aren't all the best solutions. As you know, many unintended consequences can happen when you try to deal with something at an ecological scope. Systems are complex, so there might not be one best way to deal with it. As far as international cooperation goes, you guys will read the Fragile Framework as part of your case study. But one thing that we try to do is the Kyoto Protocol. The US was a big part of trying to make that happen, writing it up, and it was a treaty to slow down climate change. But the US didn't actually end up signing it. So that's kind of a recurring theme where the US wants to hold people accountable, but when such a large player in international politics as well as in contributing to the problem doesn't sign, kind of sends a strange message to everyone else, I guess. Other ways to help aren't just with treaties, but helping other countries through the demographic transition. So giving them technology, developing countries with technology such as solar panels to transition without the same kind of ramifications of going through the whole coal age kind of thing again. We could also protect make natural preserves, such as those that protect large forests that might go across boundaries, like international or national boundaries, I guess. And that plays back to biodiversity hotspots as well. More recently, you all have probably heard of the Paris Agreement. That was signed on Earth Day in 2016. And so that's in April 2016. And just after it took effect, President Trump came into office, and he said he was going to withdraw the US from the Paris Agreement. And that happened in 2016. But he couldn't actually withdraw because, once again, the US had actually put language into this agreement that made it hard for countries to withdraw and back out on their word. So they couldn't actually withdraw until a couple of years afterward. But formally, actions towards withdrawing from that have begun as of November 2019. Of course, it's not all bad news. There are things that governments can do within a nation, not international, to fix the problem. For instance, we've classified CO2 as a pollutant. In fact, in 2009, the EPA made several greenhouse gases a pollutant. And of course, fossil fuel companies are against this. You can see how that might be true. Like if someone asked you, is carbon dioxide a pollutant? Even last year, maybe you would have been not sure what that means, but it is definitely a danger to public health. If not the most directly, at least indirectly. So it makes sense. So there are regulations there. Subsidies, of course, could encourage renewables, but also we have to stop subsidizing fossil fuels. Right now we're subsidizing both. We're giving both money. Energy is just super cheap. You don't think twice if the lights are on. But we could make energy as a whole more expensive and stop subsidizing oil so much. You can get research and development, that's what the R&D stands for, of both renewable technologies as well as nuclear. And also we can tax instead of subsidizing, so carbon taxes are just taxing carbon that comes out, versus the cap and trade system we learned about either last chapter or 2 chapters ago. But you can kind of see there's a trade-off there. If you just tax, a simple tax, obviously you pay for for all the carbon you emit. So you make money on it, every emission gets taxed, there's a price on it, it's easy, you don't have to explain it to everyone. But of course you can have your standard tax loopholes, or rich companies can just keep emitting carbon and just letting it get taxed. And of course if you say tax the carbon, you can already imagine the kind of politically charged things that would result. On the other hand, cap and trade has a limit on emissions. So remember, if I say every company can emit, 500 carbon units, and I multiply that by the number of companies, that's the amount of carbon that will be emitted. And it's worked in the past, and people don't usually have to pay it off because it creates a market for it. That said, there might not be as much of a revenue, people can cheat, Again, you have the same problem with the rich companies can keep polluting, and there's no fixed price on carbon. And, good things have happened. So, I guess on the right here, this is where we're going historically with greenhouse gas emissions, this black line. And there are lots of different models of what could happen in the future. If nothing happens, we're probably going to see 4 to 5 degree increase in temperature by the end of the century. That's a lot. That's very basically unacceptable. Currently, we're on the track for maybe 3 to 4. With pledges like the Paris Agreement, they try to bring it to maybe 2.5. Or the goal a while ago was 2 degrees. That was the hope, but that's not really possible anymore. But you can kind of see that even with the goal of max 2.5 change, it goes down over time. Will eventually come back down. So that's the goal. Some positive examples we've encountered in the past include Costa Rica. Not only do they have many nature preserves, but they're aiming to go carbon neutral by 2030. Some U.S. cities and states have done a good job of trying to reduce. California is a leader in this. Portland and Oregon does as well. In response to leaving the Paris Agreement, a bunch of states formed a coalition to try to uphold the agreement, even though the federal government would not. I think just about half, maybe over half of states, maybe just under 24 to 26 or so states agreed to this. And institutions from colleges to companies have also started moving away from fossil fuels. Of course, the question is going to be whether it's enough. So this is the last part of the case study where you can manipulate some variables to see how you can get to the 2 degree change or maybe 2.5 degree change by 2100. What would you have to do to change it? How much would we have to change as a society? Alright, so instead of just slowing down our emissions, we could also clean up what's in the atmosphere. It's not impossible. As you know, the atmosphere is a carbon reservoir, but there are ways that carbon leaves it. For instance, trees, through photosynthesis, capture CO2. That's totally natural. That can happen. Of course, we've talked about pros and cons of just planting trees. It wouldn't fix global warming completely, because there's still all sorts of fertilizer, etc., biogeochemical cycling, screwing, affecting the cycles negatively. But that's one way you can do it. You could also just fix other vegetation in general, restoring wetlands, for instance. But there are also technologies being developed to capture and store carbon, CCS, carbon capture and storage. Whether that's injecting that, really deep into the ground, kind of not making oil again, but at least burying the carbon deep enough that it won't come and bother us. But this technology is all not developed enough or too expensive, not incentivized enough to really be implemented, and people haven't really had enough time to research all the safety, could it cause an earthquake, would it escape eventually, etc., kind of drawbacks. This last idea kind of gets at the idea of geoengineering. Geoengineering is kind of using engineering on the Earth itself. So some people view it as a last resort because, as we know, every time we meddle in the environment, something unexpected happens. But there's certainly some people who make the argument that change is going to happen, we can't stop it now, unless we do something as drastic as this. We need to, because the risk management, the risk of geoengineering is lower than the risk of what happens when not if, but when the Earth warms by, 3 degrees. So whether this is, injecting particles into the atmosphere to make clouds, increasing albedo and letting it reflect away, whether it's giving the oceans iron so that algae can grow, basically mass-growing algae in the marine ecosystem so that the algae can eat up the CO2. All sorts of things like that. They get as crazy as this orbiting satellite space shield. But people who talk about this aren't crazy. It's just that they think that's sometimes the only option that we have left. Of course, this has its ethical problems, its political problems, and all sorts of unforeseen things could happen. beyond just, last slide coming up, beyond just mitigating the risk, we could also prepare for it, we could adapt to it. So here on the right are a bunch of things that you could do. So again, the biggest things being the energy use, transportation, diet. Oh, I think I talk about it in a sec, but moving away from the coast, stop building along the coast. I know everyone loves a pretty sea view, but it's just not sustainable to keep building there, and yet people do. People still live there. You know, when I lived in LA, it was also not that far from the beach. So it's just a thing that we should consider. Taking measures against storm surges. So with extreme weather will come when a storm comes, the sea kind of draws back and then kind of floods the area. That's where most of the damage comes from. So sea walls, etc. Along with other extreme weather, for instance, wildfires. Educate people, maybe train the fire department in certain things, etc. Conserving water in advance because drought will happen. And of course, taking individual changes, such as diet, so eating less meat or no meat, transportation, walking or biking, or even using public transit instead of driving everywhere, thinking about all the non-food purchases we make. The last chapter will talk about solid waste and how the way we use items is not sustainable, so we talked about it a bit with non-renewable minerals. And here is, a picture of that. So make crops that need less water, maybe GM, genetically modified. Stockpile foods in case of climate change and food insecurity that comes with it. Moving away from the coast. Stop building. Wildlife reserves should go towards the poles because as it warms up, species that currently live maybe here might want to live here instead. Hazardous waste, you can imagine what would happen if a nuclear plant were right by the ocean, but you couldn't move it because it was this giant concrete tomb and it got flooded with all its radioactive waste that gets stored on site. That's not very good. So just kind of thinking forward about it, knowing that change will happen in the next couple decades when you guys are all in the workforce and thinking about problems like these, making sure to keep them in mind. Alright, that's all for the chapter 19 notes. I'll probably hold off on chapter 21 lecture until next week sometime, as opposed to the end of this week. But with that, good luck on your case study. Let me know if you have any questions. I hope you guys are all doing well. Definitely miss you all, so hope to see you all soon. Alright, bye-bye.